Hokie dokie. Hope everyone is having a wonderful Sunday afternoon. We are going to do an impromptu exam 3 review session for 1026 students. Sorry, I did not announce this previously. I was lazy, but I figure most people just watch these after the fact anyway. So, we're still going to do it. It's just going to get uploaded to YouTube, and hopefully people can benefit from it after the fact. I have like 20 problems picked out here. They're all pretty solid, super fun problems. We're dealing with antiderivatives, u-substitution, a little bit of derivatives and chain rule, but mostly taking antiderivatives of functions, evaluating integrals. Let's get started. Number 1. So also I want to say that I will try to go through each of these problems relatively quickly. If you need more of a breakdown for any of them, though, these are all the same problems that I have posted videos for. So if you need to, just watch those if you need more guidance. But I just wanted to post all of them in this review session in one, sitting, I guess, just to show how quickly they can all be solved. I don't know. Let's get started. Number 1, they say f of x is an antiderivative for which of the following, or of which of the following. That's just another way of saying take the derivative of this and see which one of these you get. So we're just taking the derivative of this function. So we're finding f prime of x, and f prime of x will be, basically we'll have to use the product rule for the x squared times cosine of 10x, because anytime we have x terms multiplied by x terms, we have to use the product rule. So product rule says that we take the derivative of the first, so x squared has a derivative of 2x, times the original second part, so cosine of 10x, and then we add the original first part, so x squared, times the derivative of the second part. The derivative of cosine is negative sine, so we leave the inside argument the same. So cosine of 10x goes to negative sine of 10x, and then we multiply that by the derivative of the inside layer. The inside layer is 10x, so we multiply by 10. So we had to use chain rule just for that little piece there, and overall we have used chain rule and product rule. And then the plus 5 is just a whole separate piece. This plus 5 has a derivative of 0, so we can neglect it. So we're looking for this in our answer choices here. We want to see a 2x paired with a cosine of 10x. Where do we see that? We see that here, we see that here, we see that here. We want to see an x squared with a negative sine of 10x and a 10 all together. And I see that here. And that's probably it. We almost see the right term here, but it's not negative. And so we eliminate this. It's got to be C. And that's all there is to it. We're taking derivative of that function when they ask this one. That's it. Number 2. They say which of the following is an antiderivative of this. Now, if we could take antiderivatives of functions like this, then, by all means do that. But I think the approach here that they want you to do is to take the derivative of all 4 of these functions and see which derivative matches this or simplifies to this. And I'm not going to take the derivative of all 4 of these, but I will take the derivative of the first one and show why it is our answer. So we're going to take the derivative of this. So starting with this first term, I guess is what I meant, we're going to also use the product rule. So 1/2 x, we're going to take the derivative of 1/2 x to get 1/2. We're doing product rules, so we leave the second term the exact same. Now we add the original first term times the derivative of the second term. Sine goes to cosine, we leave the 2x, and then the derivative of 2x is just 2. So what we did here was the derivative of the first times the second plus the first times derivative of the second. Now we do the derivative of just this stuff here. This is not product rule. This is just the derivative of, 1/4 cosine of 2x. So the 1/4 just stays. It's just a coefficient. Cosine has a derivative of negative sine. Leave the inside argument the same. And then we multiply by 2, the derivative of 2x. And this is basically it. Now we're just trying to simplify all this down, and what should happen is it should equal what we have up here. So let's get to simplifying. What do we see? We see that we have a 1/2 times a 2 here, so I'm just going to get rid of all that. We're just going to be left with x times cosine of 2x there. And then we see a 1/4 times a 2 times a negative. So 2 1/4 gives us 1/2, but then if it's negative, we have negative 1/2 sine of 2x. And over here we have positive 1/2 sine of 2x. These go away, and we're left with that. And that matches that. And that's it. So find the derivatives of all these functions and see which one matches this. Again, I'm not going to go through all the derivatives, but that's a demonstration on why A is our answer. Let's keep it rolling. Number 3, they give us f and they ask for the antiderivative. So this is a practice in, well, first rewriting the function with the help of negative exponents. We always want to rewrite something if there's an x term or a t term in a denominator. So rewrite it so that it's in the form of t raised to some power. So now we can use sort of the reverse power rule to find the antiderivative, which I will represent with a capital F. So reverse power rule, we add 1 to the exponent. Negative 20 plus 1 is negative 19. And then we divide by whatever that new exponent is. So negative 19. We can rewrite this. We can bring the negative up top. Excuse me. Goodness. All right. Leave the 19 down there, but we're going to bring the t to the positive 19 to the bottom. If it's negative 19 up top, comes down as a positive 19. And this should be it. Let's see what we got. Negative 1/19. T to the 19th. That is option E. Let's keep it rolling. Need to drink some seltzer. All right. Number 4. In this case, in this problem, they give us a function, a constant function that is just f equals 7, and they ask for the indefinite integral of f of t. This is just another way of saying what is the antiderivative of 7. The antiderivative of 7 is just 7t. Anytime you have a constant, its antiderivative is just the constant times t. But they'll probably want plus c. So 7t plus c looks like option D. And that's it. Let's keep it rolling. This should be number 5. Again, they give us a function, and they ask for the antiderivative or the indefinite integral. So we are finding the the antiderivative of x to the 10th. We use the reverse power rule. We add a power and divide by that power, and then we add c. That looks like B. And we're done. All right, let's keep rolling. Number 6. Have a little statement 1. They say which of the following are true, starting with 1. F of t equals e to the t has exactly one antiderivative. Now, don't be confused by the way they're asking this, I guess. To say it has exactly one antiderivative would be false. Here's why. The antiderivative of e to the t is e to the t. However, when we add plus c, what that gives us is sort of a family of antiderivatives of e to the t. The antiderivative of e to the t is e to the t plus c, because you could have an antiderivative e to the t plus 7. That's one antiderivative of this. E to the t plus, I don't know, 2,000 is, oh gosh, 2000 is another antiderivative of e to the t. We just found 2, and they say it has exactly 1, so that's false. Basically, because you have plus c, there's not just one, there's infinitely many antiderivatives. Number 2, the indefinite integral of 2x plus 5 is x squared plus 5x plus c. That is true. Let's talk about why. When we add a power to 2x, we get 2, and then we divide by that 2, and then we find the antiderivative of a constant 5, we get 5x, and then we add plus c, we get this. So does this match this? It looks close, but watch what happens. We cancel these 2's here and here, and we're left with x squared plus 5x plus c. So it does match up. That's true. Number 3, the indefinite integral of f of t with respect to t represents all possible antiderivatives of f of t. That is true. So finding the indefinite integral of f of t with respect to t, that's the dt part, with respect to t, represents all the antiderivatives of, yeah, that's it, because it's like f of t plus c. Yeah, that's true. That's just a definition. So should be 2 and 3 are correct. And that's it. Let's keep rolling. Number 7. Get a little crazier. They say evaluate this indefinite integral. In other words, just find the antiderivative. Any of these constants, c and p, they will just stay in our antiderivative. So we'll go ahead and leave the c, and then we focus on what's the antiderivative of positive cosine. And that should be positive sine, because the derivative of sine is cosine. Again, the p, any constant will just stay. So we have plus p, and then we think about what's the antiderivative really of, so if we kind of split this up, it'd be like p times 1 over x. So the p got carried over, and the question is what's the antiderivative of 1 over x? And that is just ln, absolute value of x. So 1 over x goes to ln of x. We add on plus c, and we're looking for an answer like this. I think I see it in option E, but what they've done is just flip-flopped these two terms here. And that's okay, because addition is what's known as commutative. So it allows you to flip-flop those terms around that plus sign, right? All right. Hopefully that makes sense. We're going to keep rolling. Number 8. Another derivative one. Again, derivatives aren't prevalent in this whole exam material, but it couldn't hurt to know how to take derivatives. You know, brush up on those rules if need be. They say use the chain rule to differentiate or find the derivative of this function. Now to find f prime, what I might suggest for this function and other functions like it, if you have sine to the third, or I'll do another example in a sec, but if you have something like sine to the third, I would say rewrite it as sine of x to the third. And this way we can more easily see our layers when we're taking the derivative of each layer using chain rule. So then we still have minus 9, I suppose. So that's just rewriting it. Now when we take the derivative, we're going to focus on the outside layer first. The 3 power, the power of 3 is our outside layer. We take the derivative of that 3 power, so it comes out in front, and we leave the inside stuff the same, and then the exponent gets subtracted by 1 to become a 2. And again, we leave the inside term the same, so the sine of x on the inside does not change. But now what we do is take the derivative of the inside term, sine of x, and we get cosine of x, and that gets multiplied on the outside of what we have there. How's my mic doing? Is it working? Yeah, we're good. All right, just making sure. Don't want to do a whole hour-long session and not be recording. All right. So I think it's just this. This minus 9 has a derivative of 0, so don't worry about that. We have 3 sine of x squared times cosine. That looks like option B. Sorry if you can hear that fire alarm. Let's all right. Sorry about that. So we have our answer. That's just it. Again, they kind of just rewrote this term back in terms of like, sine squared of x, but again, they are equivalent. So earlier I was going to say, if you get a function like sine cubed or cosine cubed, you would rewrite it the same way. But also, if you had like an ln of x, say to the fifth, ln to the 5 of x, I would recommend rewriting that as, say, ln of x to the fifth. And then you could treat the layers and derivatives in the same exact way we did here. All right. Number 9. We are given this strange setup. The best way I can describe it is, so we're given h of x, and it looks like the result of taking a derivative using chain rule. And so what I notice is whatever's inside parentheses is usually our u, and our u is usually our inside layer, or inside function, as they will call it. So if u is x to the 1000 plus 6, all this stuff in parentheses, then the outside layer will probably be something with, like this 3 exponent. So like you would want to think, if we took the antiderivative of something to the third, we would get something to the fourth over 4, something along these lines. So this, if u is our inside function, then this is like our outside function. And I think they call it like f, I don't know, we'll see what happens. Let's go through our options here. They say the outside function is 2u to the third. Now, this is false because we said our outside function was something like this with the 4 exponents and the 4 denominator. The 2u cubed, you can see where they got that. It's in here. However, keep in mind this whole situation is the result basically of taking a derivative of the outer function. But they're just saying the outer function is 2u cubed. They didn't say the derivative of the outer function is 2u cubed. If they said the derivative of the outer function is 2u cubed, it might have been correct. But in this case, they did not. So we're going to call that false. Number 2, the integral of this function. Interesting. The integral of the entire function is this. So it's definitely close to what I have here. I wonder if this should match it. You know what? I think it would, because if I had left this 2 on the outside of this where I should have, right, so the 2 times the something cubed, or 2u cubed, we would have been left with 2u to the 4th over 4. And so if we have 2u to the 4th over 4 as the, antiderivative, the 2 and the 4 would simplify to just a 1/2 or a 2 on the bottom. And again, u is all this stuff here. So if we plug u in, we have x to the 1000 plus 6 to the 4th all over 2. And then for any antiderivative, we add on plus c. And these two are equivalent. And so I'm leaning towards a true on this one. Integral of the outside function is, that's kind of the same thing we just found. Really, it hopefully would have made more sense to do this first, then try statement 2, because we just got this as the antiderivative of the outside. And so I think this is a true statement as well. And then this is just what you get once you plug the u in place of this u here. So I'm going to call 2 and 3 true. And in this case, they say all of them are correct. Now, still can't wrap my head around this whole expression here. So they're saying f of g of x, and then this. I'm still struggling with this. I really don't know how they come up with this stuff. So I guess the integral of that function, integral of f. Okay, it's a little wacky here, but let's talk through this. So, learn from my mistakes. I haven't looked at this problem in a while, so please forgive my mistakes, but we'll at least try to justify why number 1 is correct and not false. So let's talk through it. So I've been saying that this is the derivative of something, and like parts of it is and parts of it aren't, which is kind of the annoying part. I was assuming that all of this was like an f prime. I can't do it. There we go. F prime of g of x times g prime of x, but they really mean it as f of g of x and g prime of x. And so what they're saying is like like what we labeled here, which came from this here, they really did mean that as f. And what they have, g of x on the inside matches the inside function stuff, or the u, however you want to call it. So this 2u cubed technically is the just original f, I suppose. So again, they're comparing this down here to f of g of x. So that's where like they're saying this is that, and then this 1000 x to the 999 is g prime. It's the derivative of the inside part, g, right there. So I don't know. It's a whack question, but hopefully that makes some sense why f matches 2u to the third. So learn from my mistakes. All of these are correct. Don't put too much effort on these questions. Hopefully, if it shows up, it's going to show up once. So like, don't sweat it. Just focus on antiderivatives mostly. All right. So it's always fun messing up a problem. Let's redeem ourselves the rest of this time. Number 10. For an integral that is to be evaluated using u sub, you were given u is this. Which of the following integrals can be successfully, can this u substitution be successfully applied? So what we're going to do is with this u, with any u substitution, once we find our u, we want to find the derivative of u. We want to find du. So what I'm going to do first is just rewrite our u as 3x to the negative 3 plus 1. We take the derivative of this, we bring out the 3, bring out the negative 3 times the 3, we get negative 9. X to the negative 4th. We subtract 1 from the exponent when taking derivatives. Keep in mind, derivatives coming back, I guess. So we have negative 9x to the 4th, x to the negative 4th, and then what I might do is just kind of rewrite this with no negative exponents. So really just bringing that x to the negative 4 down to the bottom as x to the positive 4. And really the trick is, like, once you find your du, hopefully some key part of du will help you identify, or like will hopefully show up in one of these answers. And if it does, that's your right answer. If it doesn't, then none of these choices is probably our answer. But in this case, what I see is a negative 9, which all of them have in some form. But more importantly, I see an x to the 4th in a denominator, which is close, but not here. Close, not here, but it is in option D. And so find that important feature of your du in your answer choice. And that's it. My man James. Yo. All right. So that was number 10. Let's move on to number 11. In number 11, they say which answer choice is the correct indefinite integral to the following function. So they want us to practice u substitution in this case. So it's almost as if they're giving us the integral of x to the 9th plus 4 to the 2000 times negative 18x to the 8th dx. So I like to just set it up like this. You don't have to, but because really it's just a u substitution problem. The u we will pick by finding whatever's in the parentheses being acted on by some outer force or outer function. And so the inside parentheses stuff is x to the 9th plus 4. Once we have u, we pick our du, or we take our derivative of u to get du. Derivative of x to the 9th is 9x to the 8th. And anytime we find du, we will tack on dx in these problems. And then we will solve for dx by dividing by, in this case, 9x to the 8th. We have our dx, we have our u. We're going to make some substitutions with this original integral here. So in place of x to the 9th plus 4, we're going to plug in u. And in place of dx, we're going to plug in this stuff, du, in place of dx, we're going to plug in du over 9x to the 8th. And now what this does is help us get almost the entire integral in terms of u's and du's, but we still need to eliminate the x terms. Now, if you've done this properly, the x to the 8ths should cancel. All the x terms should cancel, so those are out of here. And then you should be able to gather these coefficients or these constants in the mix. What we basically have is negative 18 divided by 9, because the 9 is in a denominator. So negative 18 divided by 9 is negative 2. I'm going to go ahead and bring that to the outside of the integral, and then what's left inside the integral? We have u to the 2000 du. So what we've done from here to here is successfully rewrite the integral in terms of x terms and dx terms into u's and du terms. And now that'll allow us to take the antiderivative of u to the 2000, whatever's left in the integral here. So the negative 2 can stay on the outside, but now the antiderivative of u to the 2000 is u to the 2001 over 2001 using the reverse power rule. And we'll close that and call that plus c. And then we cannot forget to plug back in the u, the x to the 9th plus 4, in place of our u. So I'll do just one more little guy here. It was x to the 9th plus 4 to the 2001. So hopefully we're looking for something like this. Let's see if we can find it here. Negative 2 x to the 9th plus 4 to the 2000. It looks like option D here. All right. I think that should be it. Here's a good glimpse at everything. All right. Let's keep rolling. That was number 11. This is number 12. Let's keep rolling. We have this crazy looking integral. And just like the last one, we want to use u-substitution. In this case, it might be a little tricky. Excuse me. It might be a little tricky picking your u value. How can I say this? We still want to pick u as the expression that's inside parentheses, and that's being acted on by some outer function. And I would say if it's inside a trig function, like cosine, for example, then this is going to be the stronger u, as opposed to picking 11x plus 12. Yeah, I'll leave it at that. So u will be this entire 11, oh goodness gracious, 11 over 11x plus 12. Once we identify u, we're taking its derivative, so we want to take the derivative of that mess there. What would help me is just to rewrite this as 11 times the whole denominator raised to the negative 1. You could use quotient rule here, and that's totally fine. I prefer to just rewrite it like this and just use chain rule. Both are valid, both get the same answer. Yeah, let's take the derivative, bring out the negative 1, we get negative 11. We leave the inside stuff the same. We subtract 1 from the exponent to get negative 2. That was the derivative of the outside layer, the outside power of negative 1. Now we need to multiply what we have here by the derivative of the inside. The derivative of 11x plus 12 is just 11. So we have all this stuff and then dx. What I would recommend is multiplying these negative 11s, or just negative 11 times 11. We get negative 121, and I'll throw this term in the denominator to the positive 2, and then dx, and then du. So this is what you would get if you did the quotient rule. And now we get dx by itself, so we'll basically multiply by the reciprocal of this quotient here. So we will get, I'm going to kind of shift it over a little bit. We will get 11x plus 12 squared over negative 121 du equals dx. So we multiplied by the reciprocal to get dx by itself. Now, what we want to do is keep our u in mind and keep our dx in mind, and we're going to rewrite this integral in terms of u's and du's. We're going to make our substitutions. We're going to leave certain things where they are for now, though. So I'm going to leave negative 66. I'm going to leave the cosine, but now everything that was inside cosine was our u. So I'm just going to write that as u. We have on the bottom 11x plus 12 squared, and then dx is all of this stuff here. So we're going to have, let's see if I can just copy and paste that. I don't feel like writing that again. Not too bad. We also need the du, though. All right. On the home stretch here, we plugged in the u, we plugged in the dx, and now we want to cancel things. Our x terms here match identically. They're perfect match. We can cancel them because one's in a numerator, one's in the denominator. Now, we have a negative 66 over a negative 121. They're both divisible by 11. The result would be 6 over 11, and it would be positive because we have a negative over a negative. So we have 6/11ths. Integral of what's left. We have cosine of u du. And that's it. We rewrote this crazy looking integral at the top in terms of u's and du's, and it's just this. So now we take the antiderivative. We leave the 6/11ths. Antiderivative of cosine of u is just a positive sine of u plus c. We write back in the u, which was that crazy quotient. It was like 11 over 11x plus 12 plus c. So we were looking for something with 6/11ths, which is the big giveaway that it's option F. And that should be it. Hope this makes some sense to anyone watching this after the fact. Let's keep rolling. Number 13. So, another u-substitution problem. It's important to recognize that this square root ends right here, and then the x to the 11th is just on the outside of that. So in this case, picking u, we will pick u from all this stuff that's inside the square root, because it's not necessarily in parentheses, but it's enclosed in some outer function, and that outer function is that square root. So the u is 2 over 3x to the 10th plus 2. I'm going to rewrite this u so that there's no x terms in the bottom. I'm going to leave it as 2/3 and then just bring the x up right here to the negative 10th. And I'll go ahead and like treat it as numerator, denominator, so I'll bring it up here. So 2 times x to the negative 10 over 3. We still have plus 2. So rewriting it like that before taking its derivative to find du, we're going to bring out negative 10 times 2, we get negative 20. Leave the x, subtract 1 from the exponent to get negative 11, and we leave this over the 3. And that's it. We call this, we tack on dx, and that's it. We go ahead and rewrite it. I'll bring the x to the negative 11 down to the bottom as a positive 11. I'm going to rewrite this too because it's bothering me. And we're going to solve for dx by multiplying by the reciprocal. So 3x to the 11th over negative 20 du equals dx. So we have our u, we have our dx. I'm going to sub things into the original integral. We're going to rewrite it. We get the integral of negative 20 on top. We have a 3. We have a square root of u, so just square root of u. And then we keep this x to the 11th down there. And then dx, this lone dx on the end up there, is being replaced with 3x to the 11th over negative 20 du. Now, what cancels? What do we have? We have 3x to the 11th and 3x to the 11th, all canceling out from top and bottom. We have we have a negative 20 and a negative 20. Those cancel. What are we left with? We have just the integral of 1 over square root of u times du. And so we rewrote this whole integral, this ugly integral, just all the way down to this. That's pretty crazy. So now we need to find the antiderivative. In order to do so, I would rewrite this as 1 over u to the positive 1/2, but then when we rewrite that, we get u to the negative 1/2 du. Now we can take the antiderivative by putting u, adding 1 to the exponent. Negative 1/2 plus 1 is positive 1/2. And then we divide by that new exponent, 1/2. Dividing by 1/2 is the same as multiplying by 2 over 1, or just 2. We have our answer pretty much, but we just need to plug back in the u, which was 2 over 3x to the 10th plus 2. 2 over 3x to the 10th plus 2. And to the 1/2 power is the same thing as the square root. So we are looking for something along these lines. And where do we see that? We see 2 square root of, looks like option A. Yeah, not too bad. All right. That was number 13. Let's go on to number 14. They say evaluate this integral. Looks like we might have like a little bit of 2 different u-sub problems. 2 mini u-substitution problems. So what I'll do first is just split this up into the integral of 7t plus 6 squared minus the integral of 2e to the 2t minus 5 dt. We're going to use u-substitution for each of these integrals. So I've split it up into 2 different integrals. We're going to do u-sub with the first one. We're going to pick our u. Hopefully it's obvious. In parentheses we have 7t plus 6, so that is our u. Du, the derivative is just 7 dt. We solve for dt by dividing by 7, so I'll just call it du over 7. And I'll go ahead and do the same for the second one here. Let's do some color coding, just a little bit, I guess. We'll say u is this stuff up here being acted on by the outer function of e to the something. So u is 2t minus 5. Du is just 2 dt. Solve for dt by dividing by 2. We have dt, we have u. Now we're going to make all our substitutions. We're going to call this equals, so in the first one up here, 7t plus 6 squared is the same thing as u squared. And then, can't forget, in place of dt, we are subbing in du over 7, which comes from here. And that's it for that integral. Now for the second one, we're going to tack on a minus. I'm going to change this to blue. It's bothering me. Alright, on the right we have minus the integral of 2e to the u, and then we can't forget the dt. We are subbing in du over 2. Now, let's see what we have. What can we cancel? So I'll just say in this first integral, we have just like a 7 on the bottom. So I'm going to pull out a factor of 1/7. And that'll leave us with u squared du. minus the integral of, I don't know why I changed colors all of a sudden. You know, I regret doing that. Let's keep it consistent. Doing my best here. Let's do 1/7 u squared du. Now we go back to green. We'll call this, so what happens? 2/2, those cancel. So I'll just cross them out. And so what we're left with is just the integral of e to the u, du. All right, not too bad. Now we take the antiderivative of each of these. So carrying it all the way over here, we have 1/7, and then the antiderivative of u squared. So that would just be u to the third over 3. So I'll just call it 1/7 times u cubed over 3. And then the second part, the antiderivative of e to the u is e to the u. We want to make sure we have a plus c. Just for both of these, we can just have 1 plus c. That's good enough. And then for the very end here, we're going to make our substitutions properly with these u terms. So we want to make sure we plug the right u back into this u cubed over 3. So that u, the blue u, was 7t plus 6. And that was over another 3. And then minus e to the u, which the green u was 2t minus 5. And then we have plus c. One quick thing, negative 1/7, or basically like 7 times a 3 in a denominator is going to take us to a 21. So what are we looking for? We want to see a 1/21th, 7t plus 6 to the third, and then just a minus e to the 2t minus 5. That looks like option B, and that is option B. All right. Let's go to number 15. Make an okay time here. Here we are given a definite integral. There's no u substitution required. It's really just finding the antiderivative and evaluating it from 1 to 2. So let's give it a shot. In order to find the antiderivative of 10 over t to the 5th, it might help to rewrite it as 10t to the negative 5, and then plus 14 sine of t dt. So antiderivative of each term, we leave the 10, we add 1 to the exponent to get negative 4, we divide by that negative 4, we add 4, or is that 14? That was 14, I thought it was parentheses. All right, we add 14, and then the antiderivative of positive sine. That should be, I think, negative cosine of t, because the derivative of negative cosine is positive sine. And we want to evaluate this from 1 to 2. Now, what I'll do, I'll just plug this straight into Excel as we see it. Yeah, we're going to do that. What we'll do first is plug in the 2. I'll just call it this. I'll say f of 2 minus f of 1. So what that means is we plug in the 2 to all this stuff, then we plug in the 1 to all this stuff, and then we subtract the 2. So I'm going to do all of that in Excel and demonstrate it. Put me down here. Move this back here. Okay. Yeah. All right. So we have equals. We're going to do plugging in 2 first. I'm going to do big parentheses. We're going to do 10 times, in parentheses, t to the negative 4. So 2 to the power of negative 4. Yeah, we're going to close that off. We're going to divide it by negative 4. We're going to add 14 times negative cosine. Now, if you have just like a negative something, negative sine, negative cosine, negative e, whatever, I recommend plugging in a negative 1. And so like instead of doing just like negative cosine, do negative 1 times cosine. of t, which is 2. And let's see if I can make sense of everything we got here. So we have 10, 14, okay, and then closing this off matches that. Okay, so that was plugging in the 2. Let's see if we can plug in everything all at once. Actually, no, let's not do that. Let's just copy this. Let's be smart. Hit enter, hit paste, but change all the 2's to 1's. So we'll do 1 to the -4, and then cosine of 1, and that should be it. So this should be the evaluation at 2. This is the evaluation at 1. Now we subtract the 2. So we just do this minus this. We get 15.73. When we look at our answers, 15.7 is an answer. So we break out the eraser and we see that E is our answer. All right. Let's move on to number 16. Which of the following is closest to this definite integral? So very, very similar process. Yeah, I don't know if I meant to include both these, but let's do it anyway. We're gonna rewrite this integral as 1 to 2, 7x to the -3. So rewriting the x term that was on the bottom up top as a negative exponent. And then adding, this should be fine as is. We'll talk through that. Yeah, so finding the antiderivative of each term, the 7 can stay. We add 1 to the exponent to get -2. Divide by -2. We add 2. E to the x has an antiderivative of e to the x. And then we just leave all the constants or coefficients around it. We just leave them alone. And that's it. We're evaluating this from 1 to 2. Yeah, I'm just going to plug it into Excel exactly how we see it. We're plugging in the 2 first, then the 1, and then subtracting them. Let's see if we can do the same thing that we did here. All right. So starting with equals 7. Yeah. Starting with 7 times 2 to the -2. Yeah. Divided by -2. And then plus 2 times e to the x is just exp to the 2, or of 2, and then divided by 3. Hope everything there is correct. Just scanning through it. All right, I'm gonna call that right, and then we're gonna copy and paste that, and just change this 2 to a 1, and I think this 2 to a 1. And we have the evaluation at 2, evaluation at 1, and because we had this in place in the last one, we already have our answer. It just subtract the 2 for us to get 5.74, 5.7-ish. And we do see 5.7 as an answer. So let's get that back in here. Looks like option C. And we are done. That was number 16. Now this is number 17. Which of the following is closest to the definite integral from 1 to 2, 4 minus 1 over x? All right, much easier example of what we have been doing. Let's evaluate. Antiderivative of 4 is 4x. Antiderivative of 1 over x is ln of x. Evaluating this from 1 to 2. Use Excel one more time, maybe a couple more times, depending on whatever other problems we have next. All right. First one, we are plugging in a 2, so 4 times 2 minus ln of a 2. We don't have to worry about the absolute values unless we were plugging in negatives. Like if we were plugging in -2, we would just call that ln of +2. So we have 4 minus ln of 2. I forgot to do an equal sign. There we go. And then we do the same thing. Do copy paste. Copy pasta. We're going to do... I'm out of it right now. All right. I guess we got 4 for that. Yeah, because we have 4 times 1, and then ln of 1 is just 0. So 4 minus 0 is 4. So we get this value of 3.3, and that is an answer. Let's bring everything back. 3.3. All right, and we're done. Number 18. I think we have a few more after this. I think I picked 20 problems to work through. Almost done though. I picked this one. It seems significant because there's a slightly different way to start this one, and the answer choices look crazy. So first step, before we evaluate the antiderivative, what we need to do is simplify this integral. Rewrite it. We'll leave the bounds, -2 to 5, and we'll basically just divide this term by x and this term by x. If we divide x to the 5th by x, it leaves us with x to the 4th, and then the 3 just stays in front. If we if we divide x cubed by x, it leaves us with an x squared. Now we can evaluate this integral. Finding the antiderivative of 3x to the 4th, we leave the 3, leave the x, add 1 to the exponent to get 5, divide by that new exponent of 5. We have plus x, we add 1 add 1 to the exponent and divide by that exponent. X cubed over 3. And now we're evaluating this from -2 to 5. Breaking out Excel. Move this over, bring this back, do that. Sorry. Just bring this over here. There we go. Boom, boom. Just gonna plug the 5 stuff in first. So 3 times 5 to the 5th over 5. Typing it in just like that should be good. No parentheses needed. Plus 5 to the 3rd over 3. And we get this because I forgot to do equals. And then plugging in -2, I'm going to copy and paste this, but anywhere we plugged in x, we're going to plug in -2. And in this case, I think we're good to not use parentheses still, only because we're raising stuff to odd exponents. But otherwise, let's go ahead, it'll be good practice. Go ahead and put parentheses around all the x terms that you plug in that are negative. Like so. I think that's it. So we get the 5 evaluation, the -2 evaluation, and this has subtracted them for us. So we have 1938.5, and that is an answer choice. It's option E. And we are done. That was number 18. This is number 19. The definite integral is approximately equal to. Now this one means business. I think this just takes some staring at and figuring out what our u term is. And in this case, if we had to pick between sine or cosine, the cosine is being acted upon by some outer extra force, extra function, and that is the square, the power of 2. And so in this case, what I would do is, honestly, it might help to rewrite this integral first, just to kind of get a visual of what we're talking about here. So rewriting it like so. So rewriting it like this, I think, helps get the visual of like the cosine rather than the sine being acted upon by this outer power of 2. The outer power, that's fun, right? All right, so now we can pick our u because we know it's just the inside stuff. So cosine of 6t. We find its derivative. We get cosine has a derivative of sine. We leave the 6t, but then chain rule says we have to multiply by 6 because 6 is the derivative of the inside, 6t. tack on dt. We solve for dt, get dt by itself by dividing everything to the left side. We have dt, we have u. Now we want to rewrite the integral. We'll go ahead and leave it from 1 to 3. We'll call this 162. We'll go ahead and leave the sign for the time being, sine of 6t. And cosine of 6t is being replaced with u, and that u is squared. And then don't forget the dt. dt is being replaced with this stuff here, du over negative sine of 6t. And I almost forgot. Thanks for catching that. We have a 6, which I forgot to divide over here. So we also need a 6 on the bottom here. All right, so now we have everything almost in terms of u and du, but we need to cancel out the t terms. What t terms do we see? We see a sine of 6t and a sine of 6t. We gather the numbers, the constants. We have 162 and a negative 6. Again, this little dot here is just multiplication. It's not any other sign or anything. It's just, okay, yeah. So we have 162 basically divided by negative 6. I have no idea. What is that? Let's see if we can do it in our heads. 60, 120, it's 42, so 27. Excel check. Let's see, 162 over negative 6. Negative 27. Did I forget the negative? I don't know. I did. I almost would have forgotten it. Negative 27. And we have the integral from 1 to 3 of what's left. We just have u squared du. That's pretty remarkable. We just rewrote this whole integral. That was in terms of t's and dt's as just negative 27 integral of u squared du. We take the integral. Finding the antiderivative of u squared, we just get u to the third over 3. We're evaluating this from 1 to 3, but before we do so, we need to plug back in the u. What was u? U was just cosine of 6t. So we have cosine of 6t, and all of that is being cubed, and all of that is over 3. And then we're evaluating this from 1 to 3. We're on the home stretch here. Again, I'll do this in Excel. Zoom out so I can drag this over. Pull up Excel, move me. That's fine. All right. So get rid of that, and that. We're going to do equals negative 27 times big parentheses, cosine, all caps, of 6 times t. So 6 times 3. We're plugging in 3 first. Close that. That's just the cosine. We want to close that and cube that. Cosine cubed. And then we want to divide that by 3 and then close that. And that finishes the parentheses. And that's it. That's the first one. We're going to copy and paste and replace the 3's with a 1. The correct 3's, that is. So we're going to, we have 6 times t, and then raise, oh, that's really just it. I only plugged it into that 1, t, and these 3's are still supposed to be there. Yeah. Okay. So we have this, which was the 3 evaluation. We have this, which was the 1 evaluation. We subtract them to get 5.37. Something feels wrong, but I hope it's not. 5.37 rounds to 5.4. That is an option. Let's see if we get lucky. 5.4 is our answer. Let's get a good look at this. And let's do this last problem. Number 20. You know what it is. We're doing a u-sub problem. We identify our u as 2x cubed plus 1. It's in parentheses, being acted upon by some outer force. We take the derivative. We get 6x squared. Tack on dx. Solve for dx. Divide by 6x squared. Get dx by itself. Get u by itself. We rewrite our integral. So integral from 2 to 4. We leave what we need to leave. So negative 60x squared over. We sub in the u. The u is squared. We'll put this negative right here. Dx, can't forget the dx here. We have du over 6x squared. We want to cancel out our x terms. X squared over x squared cancels. Negative 60 over 6 is negative 10 times the integral of 2 to 4, from 2 to 4, of 1 over u squared du. The question is, what's the antiderivative of 1 over u squared? Might help to rewrite this as u to the negative 2 du. Negative 10 can stay. We take the antiderivative of u to the negative 2. We add 1 to the exponent and divide by that new exponent, u to the negative 1 over negative 1. I'd probably rewrite that as negative 10 times negative 1 over u to the first. But then even that, negative times negative is just positive 10, and over u is just over u. Try it. Oh, goodness. So dissatisfied with my handwriting. 10 over u. But we cannot forget to plug u back in to x cubed plus 1. So we have 10. Man, none of these are to my liking. There we go. And we do not have plus c, excuse me. We are evaluating this from 2 to 4. And once we do this, we will be done. Let's open up Excel and see what we got. For all the marbles. This is for all the redemption of that earlier problem that was giving me trouble. Made me look a fool on live television. We are plugging in the 4. First, we have 2 times 4 to the third plus 1. That's all in the denominator. Yeah, that's it. All right. We're going to copy this. Copy, enter, paste. Replace this 1x, this 1 4 with a 2. Hit enter. Get these little decimals, but when they subtract from one another, we get this negative 0.51. Negative 0.51. We're going to bank on that. And we're up. Scrolling up. Negative 0.51 is what we're looking for, or even just negative 0.5. And that should do it. Let's get a good look at all this. All right. I think that was the last problem I had. Yep. 20 problems. Pretty randomized. I mean, really mostly just u-substitution, evaluating some other integrals, antiderivatives, and regular derivatives. Most important to know would be obviously u-substitution and like general basic antiderivatives, but also we saw our share of derivatives, so product rule, quotient rule, chain rule, things of that nature. So hopefully, try to feel as comfortable as you can with those. I'm going to scroll through all these problems that I worked through today, and if you have any questions, please let me know. If you have any questions that you want to see worked out or anything, or even just quick questions you would like to have answered, you can always email me at carterdmath@gmail.com. And if this session helped you. I know only a couple people are in here. I'm surprised 2 people came in at the end. Sorry, it's at the end of the session. But to anyone watching this at any point in time, if this was helpful to you in any way, or I've been helpful to you in the past, please consider donating to my Venmo at Carter D. $1 goes a long way. All right. We're going to do our little scroll through, and we're going to call it. Did 20 random problems here. Here's a look at what we worked through today. Again, sorry for not making a big announcement about doing this session. It's very, it's kind of a surprise session, but I still wanted to do it before you all had your exam, just in case you wanted something to reference, something with a lot of problems in one place, in one sitting. This is the one that gave me trouble earlier. I would not recommend watching that. Maybe watch the actual video on it where I was a little more prepared. But that's okay. Let's learn from my mistakes. That's all I gotta say. I ain't bitter. Everything's okay. All right. Good stuff there. Great stuff here. We got into the real deal u-sub problems here and here. Solid. A little split up into 2 smaller integral u-sub problems. Started evaluating integrals. We used Excel to actually calculate each of these answers, so feel free to go back and reference each of these where we actually evaluated them. Some of them quicker than others. This was a tricky one. We started it differently. We had to rewrite it first, like so, by dividing out an x from each term. And this is the last one we just covered. All right. Here's my email. Here's my Venmo. Thanks so much for checking this out. Whenever you might be watching this, I hope this helps. Again, if you have any questions, you can always hit me up, and I'll try to plan better for the next review session. All right.